In question 2, we'll be getting some practice with asymptotics. So just a quick terminology review. If a program can be both lower and upper bounded by a function, we say the program's runtime is in theta of that function. If a program is upper bounded by a function, we say the runtime is in big O. And lastly, if a program is lower bounded by a function, we say the runtime is in big omega. So in 2.1, we are asked to sort the big O runtimes from smallest to largest. So here we can see that the best runtime is constant time, the second best is log n, the third is linear, and so on. So with this ordering in mind, in question 2.2, we are asked to evaluate if the following statements are true. So the first statement has f of n equal to 20,501, and says this is in big O of constant time, meaning this function can be bounded by k, where k is some constant, which is true. In fact, we can do better and say this function is in theta 1, since it can also be lower bounded by some constant. This next statement says n squared plus n is greater than or equal to k times 0.000001 times n to the power of 3, which is not true, since as n approaches infinity, f of n will be bounded by n squared, and g of n will be bounded by n cubed. And n squared is always as good as or better than n cubed. It can never be worse. So this is false and should be big O instead. Here, f of n is claimed to be in big O of g of n, and this is true since both are bounded by 4 to the power of n. In fact, theta would be a better bound. In this next one, f of n is claimed to be in theta g of n, where f of n is the log of n to the power of 100, and g of n is n log n. In other words, is log n to the power of 100 both upper and lower bounded by n log n? And the answer would be no. Referring back to the ordering we established, f of n is just upper bounded by g of n. In this next one, we have f of n equal to n log n plus 3 to the power of n plus n, and g of n equal to n squared plus n plus log n. And we are asked if g of n is a lower bound on f. Here we have that f of n is bounded by 3 to the power of n, and g of n is bounded by n squared, which lets us conclude that g is definitely a lower bound on f. So this is true. Here we have f of n equal to n log n plus n squared, which will be bounded by n squared. G of n is equal to log n plus n squared, which will also be bounded by n squared. So since these bounds are equivalent, f of n is in big theta of g of n, so this will be true. In our last one, we have f of n equal to n log n and g of n equal to log n squared, and we are asked if g of n is an upper bound on f of n. So since log of n is in big O of n, this is false, and should instead say that f of n is in big omega of g of n. In question 2.3, we want to give the worst case and best case runtimes in terms of m and n, assuming ping is in theta 1 and returns an integer. So let's quickly walk through what this method does. It initializes j to 0 and has an outer loop running for n iterations and an inner loop that runs based off of the value of j. So during each iteration of the inner loop, we perform a constant time operation and might break out of the loop if the call to ping returns a value greater than 64. So the key thing to take note of here is that j is initialized outside of the loops, so the maximum number of inner loop iterations can be given by theta n plus 1, because we start each iteration of the outer loop with the value of j we left off with in the previous iteration. In the best case, we break out of the inner loop in the beginning of every ith iteration of the outer loop, giving us theta n. In question 2.4, we are asked to give the worst and best case runtimes where n is the length of the input array, and Mr. Poole's sort has a runtime of theta n log n. So going through this function, we have the initial call to the sorting procedure, and then a double for loop, in which for every ith iteration of the outer loop, we either terminate or iterate through n iterations of the inner loop. So in the worst case, the function never terminates during the inner loop, so we have the runtime to be theta n log n from the initial sorting, plus theta n squared for the double for loop, which is bounded by theta n squared. In the best case, we terminate early, so the runtime is given by just the runtime of the sorting subroutine, theta n log n.